last week? Hello? Why is everyone quiet today?
Yes, sir. Yes, sir.
Yes,
We're here with you, sir.
Okay, great. So we discussed linear regression last time, and we said in linear regression, your outcome of interest is continuous. It's a continuous variable. So for example, last time we experimented with age, we experimented with weight, I think, if I can recall, last week. Those are continuous variables. But with logistic regression, we are looking at categorical variables. Now, there are different kinds of logistic regressions, but when someone mentions logistic regression without specifying, then you assume that what is being referred to is binary logistic regression, right? So that your outcome variable is binary in nature. It has two options, right? But there's also what's called the ordinal logistic regression. If your data set, if your outcome variable is an ordinal data, ordered data, like what's it called? Agree, strongly agree, disagree, you know, those are ordered, they're ordered, right? So if you have data like that, you would use an ordinal logistic regression. If you have, then you also have what's called a multinomial logistic regression if you have categorical variables that are not ordered, right? So yeah, so just like if your outcome variables are, for example, colors. So you're doing I don't know, litmus test. Litmus test only has one color, or you're doing a test that the outcome can come in various colors. So green, yellow, blue. So as long as it's more than 2, then use a multinomial logistic regression. But those two are also the reason why Russia invaded Ukraine. They're bigger, they are beyond the scope of our study today. Today we are focusing on the binary logistic regression, where your outcomes are binary, either 0 or 1, either yes or no, right? So why do we need logistic regression? The preceding test, which we did before, informs us whether there's a significant difference between proportions, right? The chi-square test tells us that whether there's a significant difference between proportions, but does not necessarily inform us to what extent the variables are related to one another, allowing us to do those estimations or predictions. So just like we did the last time, we found that we were able to see, we did the t-tests, but the t-test could not tell us in any way how one predicts, how the exposure predicts the outcome, right? It can only tell us whether there's a difference between these two groups with respect to the outcome. So that's what it can tell us. So whether there's an association or there's no association with a continuous variable. But yeah, but when we now went ahead to the linear logistic, the linear regression, we're able to develop a predictive model. Do we recall that?
Again, sir.
Yes, sir. That we
I'm going to
to get the
close back to last week.
Equation.
Yeah, of course. You remember the equation, and we're able to use the equation to predict, right? Yeah. So that's what we did last. Yeah. So similarly now, in categorical variables, the analog of the linear regression is the logistic regression. Now, remember recall what I've been saying, that you do a linear regression when the outcome is continuous, and you do a logistic regression when the outcome is binary, right? I did not say the exposure.
No, they will do a PDP.
So I did not say the exposure, I said the outcome. So bear that in mind. When the outcome is binary, you do a binary logistic regression. when the outcome is continuous, you do a linear regression. Right. So logistic regression can allow predictor variables that are either categorical or continuous. So that's what I just said, right? Chi-square test and z-test to evaluate proportions cannot allow continuous predictor variables. So that's one thing. Our chi-square test, recall that when we did our 2x2 table and our chi-square test, both variables had to be categorical, right? But when we're running a regression, you could use either categorical or continuous variable as your predictor variable. But chi-square test cannot do that. So this is just telling us the difference between both of them. Then the third advantage of
Sorry, sir. Please, now that I'm seeing here that we can logistic regression can also allow us predict continuous outcomes, right?
No.
Because I'm seeing here now that continuous can predict variables that are either categorical or continuous.
No, you read wrongly. It says logistic regression can allow predictor variables, which are your independent variables.
Okay.
Yeah, not your outcome variables.
Okay.
Yeah, so independent variables are also called exposure variables. They're also called predictor variables.
Yes, sir.
Because they predict your outcome.
Okay. So now, but sorry, sir, generally, we have to use logistic regression when your outcome is categorical.
Yes.
Okay. Why for continuous outcomes, we have to use
linear regression. Yes.
All right. Thank you, sir.
Yeah. Okay. So, yeah. So, so the second part also talks about the fact that our chi-square tests that we did earlier, we did both our exposure variable and our outcome variables were both categorical variables, right? So the advantage of doing a regression, the second advantage of doing a logistic regression is that you can have any kind of variable being your predictor, right? Then you can also adjust for confounding. Do we know confounding are? Confounding variables? I think I explained that last week.
Yes, sir, we know.
Beautiful. So with a logistic regression, you can have more than one variable, more than one predictor variable in your model, such that you can adjust for confounding. So that's the advantage. That's the third advantage of a logistic model. Okay, so this compares linear regression versus logistic. Well, I think I just did that, but let's see. Yeah, I think I've said everything here now, right? So the second one says, okay, so I've talked about.
Sorry, sir. I'm sorry for interrupting. There's a statement you just made now, how we can adjust for confounding.
Yes.
With logistic.
With any regression at all.
With any regression at all. So there was something you said, I didn't get it, that we're able to use more than two variables, right?
Yeah, that's the more than one variable. You recall that with your chi-square, let me go back to chi-square. You're running a 2x2 table, right?
Yes, sir.
And you're comparing one variable, here was female, versus one variable married.
Yeah.
But as you will see soon, with your regression model, you can compare more than one with your outcome. So you can have female, you can have age, and all that. So that's how you're able to adjust for confounding. Because yeah, because I mean, whatever association, let me give a practical example. So a test was done a research was done to see the association between alcohol drinking and lung cancer as an outcome. Now, when they did what's called the by variable analysis, which is like the chi-square, looking at two variables, one variable versus a second variable, they found that there was an association between drinking and lung cancer, right? But in reality, that was not the association, right? Because when they now put that into a multivariable regression to check for confounders, they entered other variables like age, entered variables like smoking and all that. They found that the true association was between smoking and lung cancer.
Lung cancer, because even those that drink are likely to smoke.
Yes, because because in that population, most people who drink also smoke. So that was why there was a false association between drinking and cancer.
Lung cancer.
So it wasn't the drinking that was the issue; it was actually the smoking.
Okay. Yes.
Yeah. So those are the things that regression can do for you.
Yes.
Chi-square will not show you that. It just tells you there's an association between drinking and cancer. But when you now put in your multivariable regression test for confounders, it now tells you drinking was not significant, but smoking was.
Yes, sir.
Yeah.
Excuse me.
Yes.
Can we do regression, logistic regression straightforward without having to do a chi-square test?
Yes, you can.
Okay.
Yeah. So so some people do now. Conventionally, people do for some kind of research, you may see the need to do some form of bivariable regression like chi-square or just a bivariable regression. So sometimes you may have several variables you want to put into your regression model, and when there are too many, it weakens what you're doing, right? So some people would first of all do a binary like a chi-square, a bivariable like a chi-square rather, and which will help them select which independent variables they'll finally put into their final multivariable logistic model. Hope what I said was not complicated and confusing.
No, it wasn't.
Okay, great. Yeah. So So we said model. So linear regression. We are trying to compare linear regression and logistic regression. I think I already explained the point one. Point two, the type of estimates. Logistic regression predicts uses log odds and odds ratios as estimates, right? So that's one thing you'll find out. We'll talk about odds ratios a whole lot using regression. Then goodness of fit. Now, when we did the linear regression model, you can recall we talked about the R squared value, but with logistic regression, we don't use R squared. You have other means like the Cox and Snells, and there's one that is very difficult from Nagasaki or what, I can't pronounce it anyway. But so those are the ones you find them when it's run by SPSS, you would see it there as you find when we start going to the practical, right? So we did this last week, right? How to transform our continuous variable to binary variable. And then so I think, okay, well, let's do this again now because we're going to use that for the next set of exercises as we go into our regression model. So who wants to take the lead on this? Somebody. It's the same people who have been talking since. I know not everybody has SPSS, but then in terms of contribution as well, most people are quiet, and begin to wonder whether everyone is understanding. But Can someone just go ahead because we just have 10 minutes?
Okay.
So who wants to go ahead?
Okay, let me try.
Okay, go ahead, please. So we did this last week, so this should not be the challenge, but as we go ahead to the... Yeah. Oh, you weren't here last week?
Yes, but let me try, sir.
Okay, please go ahead.
So
what you're going to do, so let me explain what the exercise is now. The data set we're going to use is what? This, is it? Yeah, it's resident doctors data set. So we're going to use resident doctors data set this time around. And we want to create a new variable, right?
Okay.
We have just hold on. I want to explain before you do it.
Okay.
Right? So we want to create a new variable from hours worked, and the new variable we want to create is a binary variable. Hours worked is a continuous variable, but we now want to have a binary variable from it. Create a binary variable from it that tells us those who worked above 70 hours and those who worked less than 70 hours. So that's the binary variable we want to create now. So go ahead.
Okay, sir. Analyze. Transform.
Yeah.
We first transform our variable.
Yeah.
That's the hours worked into a binary categorical variable. Then recode into different variable. And okay, the hours worked is highlighted and is moved in. Then the name is which name am I giving it, sir?
Hours GT70.
Hours GT70.
Yeah.
Okay. Then the label, do I need to?
No, don't bother about that.
Okay, sir.
Yeah.
Then do I click?
Yeah,
change?
You change. Yeah, change. Yeah, it has changed. You can see that it has appeared here.
Okay, now. Yes, that's appeared. Then do I click on old and new values?
Yeah, new values.
Okay.
Yep.
So range through the.
Yeah, because you now want to have those who are 70 and above.
Yes.
So you range through highest.
Range through highest. Okay.
Yeah. So the highest value you want, you want it to be higher than to be 70 higher, right? So you put 70 there.
Okay.
Yeah.
70.
Yeah. Then you go to new value.
New value.
Okay. Yeah, we're creating the binary variable. So everyone who is 70 and above becomes 1.
Okay, 1.
Yeah. Add.
Okay, then
add. Yeah.
Okay, add. Yeah.
Yeah. Good.
Yes.
So then you now we want not yet. Not continue yet. So you now want every other variable to be 0.
Yes.
So go to the left down there, you see all other values.
All other values. Okay.
Yeah. Then you go back to value. Go back to value. 0.
0. Okay. Then add.
Yeah. So you see, wait, hold on. So you can see now it has told you that
else
7 through the highest. That 7 to the highest value would be 1, and then all the others are coded as 0. So it's not a binary variable. So continue.
Okay.
Click continue.
Continue. Change. Okay.
Yeah.
Okay.
So you can see that. Good. So what we want to do now, let's go to variable view.
Variable view. Okay.
Yeah. Make that 2 decimals, change it to 0 for our new variable. Yeah.
Change to 0.
Yeah. Okay. All right. So go back to the data view.
Data view. Okay.
Okay, beautiful. So it's now 0s and 1s. Good. All right. So the next step would be you want to create your 2x2 table. with percentages.
Okay, analyze, descriptive, cross tabulations, then the variable again, sir. Sorry.
Okay, so we created a new variable called hours 70, right?
Yes, sir.
Hours GT7.
So we want to compare. So our question here is to find out whether there's any association between being female and working above 70 hours.
Okay, sir.
So
being female and working above 70 hours. Okay.
Beautiful.
So the statistic we use chi-square is already selected, and then continue. Then the cells.
Okay.
The whole percentage has been selected. Continue.
Okay.
Then I will click OK.
Yeah.
So I have to stop sharing and share the output.
Okay. Beautiful. Yeah. So we can now see our chi-square. We have our 2x2 tables, which we have discussed before. But for want of time, we won't go through all that. But what does our chi-square tell us?
The chi-square tells us that our Pearson chi-square is 5.593, and it's less than 0.05, which means
p-value
that
is less than 0.05.
P-value is less than 0.05, which means that we are going to we are going to reject our null hypothesis. If we fail to accept our null hypothesis,
you can you can reject your null hypothesis here.
Okay, we reject our null hypothesis, and then this tells us that there's an association between the hours more than 70 hours worked and being a female. So
typically conventionally you state your exposure first before your outcome. So there is an association between being female and working greater than 70 hours, right?
Okay.
So the next thing we're going to do, we're going to now do the regression now.
Okay.
So you go to analyze.
So let me close and can I go to analyze from?
Do that. Let's see. Look, there's analyze there.
Analyze. Then can you
regression.
see me?
Yeah, we can see regression.
Okay, regression. Then
so what kind of regression are we doing?
Binary logistic.
Beautiful.
Then the dependent variable here is hours worked. Hours 70. Good. 70 hours worked.
Good.
And the covariate here is the female. Do I add other covariates?
No. We're just doing one exposure at this point. So categorical. So you're already very familiar with this now. Go ahead. But explain so that everyone will understand. So go close it first so that we want everyone to follow, please. Because I can see that you already know what to do.
No, it's just self-explanatory, sir. So I clicked on categorical.
Why are you clicking on categorical?
Why did you say self-explanatory? You want to throw atomic bomb?
Okay. I saw categorical, and I think I should be able to select the variable that is categorical here.
Yeah. So this is the thing. Recall that our covariate, like I explained initially, that with a regression, your covariates can be continuous or categorical.
Yes, sir.
So in this particular case, we have a categorical covariate, right? So we need to tell SPSS that what we have, recall that the number that SPSS is seeing, this female you're seeing here, SPSS is seeing it as 0 and 1. You understand? It's analyzed as 0 and 1. So and 0 and 1 could be continuous as well. Yeah. But so you need to tell SPSS that it is actually a categorical variable. Yeah.
I get it. So we select categorical.
Yeah.
And then we tell SPSS that female here is categorical.
Yeah. And then So basically we have the indicator as well. We want the, no, it's okay, leave it that way. We want the reference category to be the first, right? Okay. Now what that means.
Now what does that mean?
Yeah, so that's what I'll explain. So all this you're doing right now, it's good because if you're using Stata, for example, you just enter codes and it does that quickly for you. But now with last week we were not able. Okay, we didn't get to that stage. We ran out of time. We didn't talk about dummy variables, right? And yeah, so but when you have categorical variables, what SPSS wants to do is it will now be to compare, right? It wants to choose what category you want to compare your analysis with. So when we are interpreting now, we want to say, okay, in comparison to males, this is our outcome, right? So we want to choose the variable, the category of our indicator that we want to be our reference category when we're analyzing. So
the first here, does it mean 0 or 1?
So the first here means 0 because 0 is before 1. So it goes in ascending order, right? So first is 0. 1 will be last in this case, but in certain cases you may have, if you're not even be binary, you could be, it could have 3 or 4 categories. So yes, yeah, so so the first one is always the lowest, and the last one is the highest number that you coded it with. Any question? Any confusion about this? So
now, if you now want to report this now, are we now saying
we'll report? Let's get to reporting, and then you'll see what I'm talking about. Okay, we've not reached there. You're jumping the gun. But does anybody have any confusion about this? Okay, go ahead. So continue.
Okay, you can continue.
Now recall that when you one thing, when you whether you choose first or last is not an issue. I mean, you can choose last and it still gives you a result, but the way the odds ratios will be different because you're comparing it in the opposite direction, right? So the numbers will not be the same, but the significance will be the same. Just the way you interpret it that will change. Okay, so yeah, so okay, right?
Okay.
Yeah. Good. So here we have our logistic regression output. The first one is just your descriptions and all that, right? So let's keep going. Let's go down. Yeah, forget about all these. These are just coding, how it's coded, and we don't need this.
The categorical variables.
Yeah, so it just tells you about the 2 variables you have and all that. Classification. Let's scroll. So variables indication, variables not indication, your test of confusion and all that. So yeah, then this is what I talk about, your Cox and Snell R square and your Nagel-Keke R square, and that's what I was trying to. That's on Nagel-Keke, Nagel, whatever. Pronounce it how it suits you best. Yeah. So those are the, unlike the R square you have with linear regression. Logistic regression uses Cox and Snell, Nagel-Keke. That's another one, but there are still others as well. But SPSS reports only these 2, right? If you're using Stata or using R, perhaps you have the other ones reported as well. I don't even know. Perhaps you could even select them in SPSS. I've not tried that before. Maybe there are other options in SPSS if you go further here. I didn't look at that. Okay, so we want to look at variables in the equation, right? So that's our major output here. So you can see that it tells us here. Now we have various okay, you know what? Let me share my screen. Right. so that I can show you how